All right. Yeah, I think it's time for us to start. Um, so first of all, don't hesitate to ask any questions. Please post them either in chat or like in Q&A section. We will answer all of them, but at the end of the presentation. And yeah, so I will just now mute you all, but feel free to type something in chat. I will be kind of checking chat in just in case if like sound will drop or something like that. So yeah, feel free to use the chat. So okay, let me introduce myself. So my name is Andrei. I'm an Android developer, and in Android I since like 2017. Before that, I was also a programmer, but I was programming in a different language. And yeah, in Android, I love building animations actually. So that's why I think this talk could be interested. Um, And what's our agenda for today? So first of all, we will discuss animations. Why do we need them? And what is considered a good animation and what is considered as bad animation. Then we will uh, discuss animations in Android views. What problems do they have? What why they were convenient and why they were inconvenient at the same time. So what are their advantages and disadvantages? And we will discuss the Compose provided API, right? So what animations can be done using Jetpack Compose just out of the box. And we will discuss like a high level and the low level APIs that Compose provides us with. And we will just like briefly compare performance of the Jetpack Compose animations versus the view-based animations. And we will figure out how to cover animations with tests. And in this talk, we will start with like simple animations. We will figure out how to rotate, change colors, visibility of composable functions, and we will develop more complex animations towards the end, um, like using transitions, and we will discuss also drawing on canvas. So first question we need to answer is why do we even need animations at all? So often we think of animations as just of something that is nice to have, and that is something is not critical to be present in the application, and as of something that can be done at just the end of the development cycle. But actually, don't forget that animations are a very important part of the user experience. They help the user to understand what's actually happening on the screen and where to direct their attention. And you can see from the example that GIF image on the left, where the animations are enabled, is much nicer and cleaner than the one on the right. And the next question we need to answer is how to do well, right? So what is a good animation, and what characteristics does good animations have, right? So the first sign or first characteristic is that good animation must be re-entrant. And if it's a bit confusing, we can understand it using the following example. Probably in like all presentation layer architectures, be it MVP, MVVM, or MVI, there is an entity that is somehow changes the view, right? So in MVP, this is the presenter. In MVVM, this is a view model. In MVI, it's some kind of store, right? But all of these are in common that this entity somehow changes the view state. And while the application is running, this entity changes the UI state of the application. And these changes can actually occur at random intervals, right? So, for example, user pressed a button and application needs to react to it, or like a response came from server, and we also need to kind of change the UI or react somehow to this event. On the other side, we have a view that is essentially a consumer of this state changes, right? So, and let's take a step-by-step look at why and how this is happening. So somehow view state changed, and our view consumed new state, and we, like a good developers, reacted to this change of state, and we launched the animation. And then after some random period of time, we again received a change in state, right? So a new state comes in. And we want to react it somehow to it. But what should we do if the animation that we have already launched is still in progress? Obviously, we must somehow react to it, such as, for example, we can interrupt running animation or cancel it or start the animation in a different direction. And this what we mean when we talk about reentrant animations, right? So reentrant animations are those animations in which we can somehow react to change in state, and we can interrupt or cancel an animation that is in progress, right? So we cannot just launch it and forget about it. So we need to react to state changes with the animation. The second sign of good animation is that the animation must be continuous. And here is an example of a square that increases and decreases its size by scaling, right? And everything is fine actually if we run the animation in the opposite direction after it's completed. So we kind of clicked make big, our square became big, and we waited for it to be big, and then we launch it in the opposite direction and we launch it to be small, right? But what happens if during the animation process we want to cancel it and start it like on the opposite direction? And here we see that this animation is already re-entered, so we can react to state changes, right? But still, we can see if we just change the direction of it, we can see this glitch, right? Let's figure out why this glitch is happening. So you can see that animation is not kind of smooth, right? So animation is essentially a smooth change of some value over time. And in our case, we change the scale of the square, right? And when the animation progress reached 60%, we decide to run it in the opposite direction. But we launch it not from intermediate value that animation currently reached, so not from 60% of the animation, but from the terminal value from 100%. And that's why this glitch kind of happens, right? So because we have this difference between like the values of which we launched this animation from, right? So our animation finished like interrupted at 60%, and we launched it back from 100%, not from 60%, right? And if you think that this is something that happens just in theory, here's a real life example. Here is, you can see like iOS screen on the left and Google Pixel screen on the right. And I do exactly the same, right? So I open the folder and then cancel opening it by tapping somewhere outside, right? And we can see that iOS handles it well, right? So iOS handles it as is like a good animation, right? So it cancels scaling of the folder and reverts it back. While the Google Pixel, for instance, it just launches the animation from terminal value, and that's why we see like this glitch in animation of Google Pixel. And Google Pixel handles this case incorrectly. And I guess you can agree that the one on the left looks nicer than the one on the right. So, and if we take this kind of knowledge into account and we fix our code and we start animation from the intermediate value, then everything immediately falls into place and starts to look much better. So we can change the direction of the animation at any point of time, and we can see the animation kind of running smoothly, right? And the final sign of a good animation, or like icing on the cake, is how smooth your animations are. Let's take a look at this example. Here, a square flies to the upper left corner when I press the top left button, right? And please note that I press it 2 times. And at the first, animation goes smoothly, but during the movement, like when the animation is still in progress, I press the button a second time. And despite the fact that the square continues to move to the same corner, a slight lag occurs. You can see it, right? So it looks like our animation kind of starts over. Or another example, if we first launch this square into upper left corner and then into upper right corner, and then again we can see small lag or like a glitch, right? So when square changes direction of movement. And it looks like this is not like one smooth continuous animation, but it looks like two animations launched separately. And this happens because due to the fact that another important characteristic of the animation is not preserved. It's a speed, right? So when animation speed reaches a certain value, for example, 60% of the maximum value, we start animation again. And because of the speed is reset to 0, we need to accelerate again. And because of this, we see such a small lag. And this actually is like very well-known problem in Android animations framework. And actually, Google in 2019 introduced a library aiming to fix this. And this library provides the opportunity to implement so-called physics-based animations. So the animation that kind of tries to imitate the laws of physics. And basic concepts here is a spring, its stiffness, and the force with which we can stretch or compress the spring, right? And if we apply this kind of physics-based approach to our animations, we will see that the problem has now disappeared. So no matter how many times I press the top left button, the square continues to move smoothly to the top left corner, right? Or in the other example, if we change the direction of movement of the square, then there is no lag. Everything looks natural and kind of pleasant, right? But unfortunately, there are problems with it too. So Google presented this library, like physics-based animations library, in 2019, and now the latest stable release is 1.0.0. So it means that it was never updated in 3 years, and seems like it will never be updated, right? So we can assume that it's abandoned. Now let's remember animations on regular views and discuss what's wrong with them. So first of all, many ways to run animations in view system, right? And all these ways are often conflict with each other, and it's not always clear which method is the best to use. So some of these animations partially correspond to the principles of a good animations that we've discussed, but some don't, and we have to implement it ourselves. And it's also not very convenient to combine them with each other. For example, if you want to use like layout transition with view property animator, you might encounter some like unexpected complexities when you try to develop that. Also, we have a bunch of problems. First of all, we make our view stateful, which means that we have to store the like animation state somehow. We have to keep references to object animators or value animators. Also, there is no convenient way to manage it out of the box. So in order to animation to correspond to these characteristics of a good animation that we discussed, and like intermediate animation value must be stored somewhere, right? So when we launch animation, we must store it like intermediate value somewhere to launch like second animation from the intermediate value and not from terminal and stuff like that. Also, we need to handle rotation somehow. And one of the most important things, we have to kind of launch animations only, like we need to launch certain animations only when the view is attached to window. For example, if you try to change layout parameters of a view when the view is detached, for example, launching like some size change animations, the application will crash, and you have to kind of keep track of whether view attached or detached from window. And also memory leaks can occur, right? So when animations launched, we often add all sorts of listener to monitor their progress, and these listeners might not be removed correctly, and we might leak some view context through them and stuff like that. So yeah, also not very convenient. And I would like to kind of summarize what we've discussed in this section of the presentation. So the foundation of a good animation is re-entrance. So we must be able to somehow react to the changes in state of the view during the animation process. And without this property, animation cannot be considered a good animation, right? So second kind of sign of a good animation is the continuous. So animation values should change without any gaps, and without being continuous, animation cannot be smooth. And if your animation matches all these three signs, you can be sure it's a good animation. Good news for us is just that Jetpack Compose is designed in such a way that most animations meet all these requirements, right? And not all, but most of the Jetpack Compose animations are considered like a good animations, right? So we can say that they are in general re-entrant, continuous, and smooth. And for those animations who don't comply with this signs of a good animation, Jetpack Compose API provides opportunities to implement this quite easily. And now we are diving into Compose world. And first thing you see when you're trying to dive into Compose animations is this diagram. And it may seem overwhelming, but if we hide all the distracting things from this diagram, we will end up with a small set of different functions and classes that help us as the developers create animations of any complexity. So therefore, now we will go through the main elements of the API. So if we group these elements, like roughly group, we can kind of see following groups, right? So first one is like basic API. It is like a high-level API that we use most of the time, and it will be sufficient for like a lot of cases. Secondly, we have a low-level API. This is more flexible API on which all basic animations are built on. And the third part is the animation spec. It's not like animation, but animation spec is a part that is responsible for customizing animations. And animation spec is used almost everywhere, and we will see it almost in every function. And in some examples, I will just omit it for just simplicity. And let's start with animated visibility. Animated visibility is one of the easiest way to create animations in Compose. And animated visibility is, as everything in Compose, composable function, right? And it animates appearance and disappearance of the content, as we can see in this example. So animation occurs when isVisible state changes. So isVisible stored in a mutable state, and when new state comes in, we change visible property, isVisible property, recomposition happens, and animation starts again. And now let's take a look at the function definition. And here we are interested in two parameters. Enter and exit transitions are in essence a way to declaratively describe the appearance and disappearance of the content, right? So the default ones are fade in, expand in, shrink out, and fade out, and they are provided by the framework, by Jetpack Compose, and we do not have to implement them ourselves. And on the right, you can see an example with using scale in and scale out, right? So we kind of have this animation of the cat. And yeah, and this is what can be done just by using framework provided enter and exit transitions. And if this list is not enough, you can always combine several of them by yourself. And you can simply add them using the operator plus, and we have like completely new result. And you can see in the example, if we add fade in plus scale in, we have this beautiful animation. And it's like, I would say it's relatively complex. And so yeah, we can combine these enter and exit transitions and create completely new animations. But can we somehow customize this enter and exit transitions? If we look at the source code, enter and exit transitions are actually sealed classes. That means that we cannot develop our own implementations that the ones that provided to us by Jetpack Compose. Fortunately, we have a way of customize almost any animation, and this is animation spec. So animation spec can be used to customize almost any animation. Animation spec is used almost everywhere, and Jetpack Compose provides us with several different implementations of the animation spec. We'll take a look at each of these individually. And let's start with like a simple animation. This point moves from start to finish and back. We can do this by using Twin animation spec. And here's how it looks like in code. So Twin animation spec is duration based, which means that animation will be running for some time. In this example is 1500 milliseconds. Also, Twin has start and end values, and animation kind of moves between the start and end values. And we can customize animation spec with easing. Easing is a special thing that is kind of similar to interpolators in Android, but you can see that in the following example, right? So we have like two lines here, and they are moving differently, because they have different easing. So first one is kind of feels more natural and alive, while the second one feels more mechanic, and this is because we used linear easing with it. And this is actually easing responsibility. So and as I said, if you have some experience with views-based animations, easing is like interpolator. So easing is responsible for value of the animation at different points in time. And in this example, you can see it more clearly. So first easing is fast out, slow in easing, and second one is linear easing. And on the graph, x-axis is a value of the animation and y-axis is time. As we can see from the graph, the blue dot accelerates slowly at first and slows down towards the end, while the red one moves at a constant speed. And that, in essence, is easing. And here is like more examples of the kind of main or most common easings that provided by Jetpack Compose. And this doesn't mean that we can't create them ourselves. And yeah, basically we can create our own easings. If you want, you can do that. And second kind of big thing, as opposed to Twin animation spec that we've just discussed, which is duration based, we also have a Spring animation spec, and animations that you are seeing now looks very similar to the previous ones, but there is an important difference. Spring is the animation spec for which you cannot specify a duration, and the animation spec tries to imitate a spring. So spring is not a duration based, right? We cannot set a duration here. And here we are interested in two parameters. Stiffness. To simplify, stiffness is responsible for the speed of the animation. And the second one is damping ratio. It is responsible for how bouncy, I would say, your spring is. And let's take a look at the example. They have like different damping ratios. So for first one has no bouncy, and we can see that it's not like bouncy at all, right? So then we have second one is a bit bigger, third one is a little bit bigger, and the first one is even stronger bouncy. And please also pay attention to the following things. Since the duration of the animation is not specified, easing cannot be provided here, because easing is dependency between time and value of the animation. Since there is no time, we cannot provide an easing. Also, animation can go out of bounds. But the main thing that Spring animation spec guarantees to us is that by the like at the beginning and by the end, animation will be returned to the start and end values respectively, right? So when it started and when it finished, it will be guaranteed by Spring to us. And this was kind of all in relation to Twin versus Spring. And now let's take a look at what other neat things Compose provides us with. We also have a neat way of repeating animation, and repeatable will help us doing that. We have a regular repeatable and infinite repeatable. Both of these animations can only work with duration-based animation spec. So, for example, Twin. And regular repeatable, you can also set number of iterations in it. And this can be most clearly seen in this example. Repeatable stops after 3 iterations, and infinite repeatable never stops, as expected. And we also can specify repeat mode, so to either restart the animation or reverse it to the opposite direction. So instead of restarting the animation, reverse returns from the final value to the initial value. And note that the repeatable animation ended after 3 transitions, so which means that kind of going back is counted also as additional iteration. And the last one is snap. It just instantly switches the state without any animation. So yeah, it's just like instant change in state. So we've looked at the basic animation specs, and now that we've got those things out of the way, let's get back to animated visibility. So as we've discussed, animated visibility is one of the simplest and at the same time not very flexible components. All it can do is just simply animate visibility. The state it operates with is just like a Boolean state, like a true or false, visible or not visible. But what if we want to switch between a different state, like different states, right? Not only true, false, but to more complex ones. And now we will dive into animated content. Animated content is like I would say, a relative or a brother to animated visibility, like older brother, right? So, but as I said, while animated visibility allows you to animate visibility of the content, animated content allows you to animate the change of the content in a more flexible way. Let's look at the example. So this is what the most basic example looks like, right? So we increase the counter value and our line inside text changes. And we are doing that using animated content. So animated content has a default transition spec. In this case, it's fade in and fade out. And thanks to transition spec, we can specify more complex animations when we changing content. Now, when changing content, it moves from left to right. But there is something wrong here. You can closely look at this frame, and although animation moves from the left and goes to the right, it seems like it's like cut off, right? So this happens because the animated content is trimmed to the size it will be after the animation is complete, right? And even if more space is needed during the animation process, we will still kind of trim to the end value. And to fix this, we will need to add size transform to this animation spec. Yeah, and now we see that the animation now seems to go beyond the boundaries of the zone. And instead of animated content, you can use simplified, but like a version of it, a crossfade, and it can do just like change of content with just fade in and fade out. So a quick summary. So far, we have covered the following topics. We covered animated visibility, animated content, animation spec, and the next big thing and very convenient function in Compose is the animate value as state functions. So using animate float, in this example, we will use animate float as example as a function, and we will animate change of the alpha component of the text element. So when a visible kind of variable changes, target state also changes. So it will be changed from 0 to 1 f and back if visible changes, and animation will be started. As a result, we got something similar to animated visibility, but alpha here is explicit parameter that we pass directly to the modifier, right? And this means that we could control like our animation more, right? So we can pass not only alpha, but we can pass colors and stuff like that. So and Compose actually provides us with following types out of the box. We can animate float, colors, DPs, like sizes, offsets, and stuff like that. And each of them is used like similarly to previous example, and we can also develop our own animated state functions animated different things, for example, like rotation. Now that we understand what animated state functions do, we can combine multiple animated state functions into one animation. So what happens if you animate color, size, and rotation at the same time? And you can see the final result right away. And it turned out to be a square, just animates from red to blue. Its size changes and its rotation changes. And let's see how easy this animation is to create. And the following code will help us with this. So initially, it's just a red square. And this is just like a regular composable function. It doesn't know anything about the animation, and its job just to draw the color, size, and rotation of the square. And we will animate it from the outside. So we can have only two states, active or inactive. So we use mutable state where we will store this value. And since we haven't added any animation yet, we will display a red square without any animation, with just our default values. And let's us add first animation. So with just like a few lines of code, like 2 lines of code, we added this color animation. And we can see that color is animating between red and blue. And again, it's animating when the active state changes. And this animation actually corresponds to the principle of a good animation that we discussed. So it's re-entrant. So we can launch it to the opposite direction while it's still running, and it will animate back to the needed color. So it will not jump, like there will be no jumps. It will be continuous animation. So yeah, it's a good animation in terms of the kind of principles of the good animation that we discussed. Let's add a change of the size. Again, pretty easy. Depending on the active state, our square will change from 60 dp to 150 dp and back. This is also good animation. And we will add a rotation. It will also rotate from 0 to 180 degrees. And in fact, we can stop here, but that's actually not it, right? So the approach has several problems. And the main one is there is no explicit previous and current value, right? So, I mean, in terms of state. So we cannot simply find out from which state animation is switching. Because of this, with the increase in the number of states and transitions between them, we have no way to monitor from which state the transition occurs. So for now, we had like only one Boolean state, but we can have multiple, and we won't be able to check what state we are starting our animation from and what state we are targeting our animation from. And to make it more clear, let's look at the following example. So we have like a simple animation. You can see that like several icons, like home icon, which represents home, like this uh, star icon, which represents movies, and the icon that represents work. And we have a blue dot, a man basically who transitions between home, work, and movies. And the animation itself is like pretty simple. I have omitted all the code except for the one that is responsible for animation itself, and you can see it on the right. Here we use animate offset, int offset as state to properly animate the position of this blue dot. But what happens if this example become more complex? So now our little man is very tired after work and wants to go home so much that he will get home 4 times faster. So before that, every animation took like 2 seconds, and now when we go home, we want to go like at 500 milliseconds, so 4 times faster. And this can be done pretty easily. We can just add what state we are currently targeting and change animation spec respectively. But unfortunately, this code has one significant side effect. From cinema, our man will also go 4 times faster. So we only wanted to go faster from work, right? So, but because we only stated the end kind of end state, we will also run home from cinemas also 4 times faster, but we don't want that. But can we do something about it, right? Of course we can. And we can do it with animated state functions by introducing like some previous state. For example, if we are moving home, we need to store somewhere that what was the previous target state. For example, we are going home from movies, and but actually on a big scale, if we will use this approach will add us a lot of complexity, and it will basically eliminate all the profits of using animated state functions. And moreover, Jetpack Compose has a neat way of solving such type of problems. Meet UpdateTransition. Let's try to refactor our current implementation with UpdateTransition. So first thing we need is to create UpdateTransition with our state. And UpdateTransition is just a composable function that creates and stores transition object. Then we change animate int offset as state to transition animate int offset. And please note that in transition animate int offset, we have a lambda with a target parameter, right? And this lambda will be called each time when we are changing the state for calculating new target value, which our animation should target to. Now, the only thing left for us is to add duration of the animation. And this is done using transition spec parameter. And now we can just apply different animation specs to different target values. And we have a neat way of doing that by transitioning to function, which allows us to check what state we are currently in and towards which state we are processing our animation. So, and if we check this function source code, it just checks this and current state. As a result, we have this pretty complex animation, and all of the code to create it is more or less like 20 lines of code, which is pretty neat. And now let's talk about additional features of the transition class. First one is the transition has built-in animated visibility. It also has built-in animated content, and it also has built-in crossfade. So also we can be encapsulate transition and apply it to a different objects. And here's the animation of a square, and here's the same animation of an icon. And transition frameworks and transition framework allows us to conveniently reuse already created transition between different objects. So a quick summary: by now we have covered the basic API and the animation spec. This means that we have to go deeper and see how it works under the hood. So if we recall animate float as state functions and all of other animate as state functions, all of these functions are actually internally use animate value as state function. And this animate value as state function internally uses animatable object. But what is animatable? So in animatable, we are only need to focus on two things. First one, that is animatable is stateful. And basically animatable is a state holder for value, like for generic value, right? And the second one is animatable is working using coroutines. So it has several fields and methods, and we are interested in suspend functions and how to use animatable. Let's look at the example. The first thing we need to do is to create and remember animatable object. And below, we see that now our strip is simply drawn in its like original state. So we don't have any animation yet. To use animatable, we need a coroutine scope. We created by using launched effect, but it can be created like using different methods. Here we're just using a launched effect. And inside, we only have a while true loop. All that remains for us is just to call animate2. And despite the fact that we inside loop, the animation is not repeated. And this happens because animatable has cached the value internally. And now calling animate to 1f will not animate because we already kind of animated to 1 1f, right? And there is no change for us. So once we animate it to 1f, we will not animate it again. So therefore, we need to reset the value. And if we add snap to 0f, we will kind of have this infinite repeatable animation. And now that we've covered animatable with an example, let's go even deeper. We have methods animate2 and animate decay. One animates by duration, and the other one animates kind of decay, right? So we have like initial value, and we will animate to some like to 0. And this is like pretty similar to twin animation spec and spring animation spec that we've discussed. But inside this animate 2 and animate decay, two classes created, two objects created, right? So target-based animation and decay animation. And both of these objects are actually kind of children or extend animation interface. And animation is actually the lowest level API available to us. And for now, all we need to know is animation is stateless, as opposed to stateful components that we've discussed. But what does it actually means? And it means that animation doesn't store animation value, but instead it's calculated for like a given time, right? And it will be clear from the following example. So if we take a look at the source code, we have a bunch of methods, and we interested in get value from nanos, right? So this method basically takes some time and it returns some value of the animation. And the scheme, how it works is like we have some time of the animation, we pass it to the animation object, and if we call get value from nanos, we will basically receive the value of our animation. So the scheme is pretty simple. And now let's take a look at the following example. We have a heart animation, and this heart changes its state from 0 dp to 100 dp. So if the time of the animation is 0, we will get 0 dp in size. If the time is 300 milliseconds, we will have like 36 dps, and for 1000 milliseconds, we will have 100 dp final value. So this is expected. And we have like two fundamental ways in Jetpack Compose to achieve similar result. First one is target-based animation. So the animation where we have initial value, target value, and the time or duration of the animation. And the second way of achieving that is using decay animation. And instead of target value and time, we have initial velocity. This means that animation will decay from initial value with initial velocity to velocity 0. And as a result, we will have the same hard animation, but it's just like same hard, but it's animated in slightly different ways. But in this case of decay animation, we didn't specify the duration of the animation and its target value, but we only specified initial speed and initial value. As a result, we have like a different intermediate and final values of the animation. And now we've discussed most of the Compose provided API animations. There are only couple things left, and now we will switch to curtain-based animations. So a use case for curtain animations might be if you want to launch several animations sequentially, one after another, right? And then combine it with some parallel execution of the animation. And in this case, you might want to check out the curtain-based approach. So imagine that we have suspend function animate, which animates something. And if we want to launch two animations in a sequence, we would just need to call this animate function in a curtain scope 2 times. And the second animation will be started only after first one is finished. So they will be executed sequentially. For parallel execution, we can launch new curtains that will work in parallel. And we can also combine two approaches. So we can use curtain scope to launch two animations in parallel, wait for their for the end of their execution, and then launch two different animations in parallel, right? And this allows us to build and create very complex animations easily. And let's take a look at some code and create one more animation using a discussed approach. And first thing is we need to create animatable object. Then we're creating and remembering curtain scope and launching our first animation. Here we have a heart that is increasing its size to 300 dp. After that, we want to animate heartbeat. So we want to launch that sequentially only after first animation is finished. So we are using the same curtain scope and we are not launching new curtains. So number 2 on the slide is the heartbeat animation that is also running sequentially. And then using new curtain scope, we launch two animations in parallel. First one is we reduce the size of the heart to 0 dp. And the second one is we change the vertical positions of the heart. And when both of these animations are finished, we only need to reset the state using snap to function, which will also happen sequentially after all of this is finished. And after that, we can safely call animation finished callback if someone is listening for the finish of the animation. So in just a few lines of code, we created this pretty complex animation, I would say. And I think it's a win for Compose, to be honest. So now we've covered all the basics of the Compose provided API. And of course, there is more to it. And feel free to discover all the interesting things and edge cases by yourself. And now we will try to apply our knowledge to create not so obvious things. Yeah, I just noticed the time now 152, and we have about like 185 of them. So we are pretty close to the end. Another important part that we haven't discussed yet is drawing on canvas. So now we will figure out how to make such animations like of a bouncy rope. And please also note that there's also processing of touch gestures, right? So we can kind of touch this rope and animate it with our touches. So we can start by implementing a point that we can drag around the screen. The point is like all UI elements in Compose, is the composable function. So in our case, with two parameters. The first one is the size in dp, and the second one is mutable state offset, right? Offset is essentially the coordinates of a point inside its parent, and offset is wrapped in mutable state so that when it changes, recomposition is called. And the state itself is stored above so that it can be shared with other composable functions, right? So it's like a pretty common principle in Compose to hoist the state, and it's called state hoisting. So the point itself is just a round-shaped box with a black background, and here we are interested in two modifiers. The first one is an offset that reads values from the mutable state and draws a box at the given coordinates. The second one is pointer input. This is similar to a touch listener in the view system, and inside a lambda function, which we get, so inside there is a lambda function in which we get how much the drag amount has changed. So then we add this change to our offset, and after that recomposition is called, and the point is redrawn with the new coordinates. Now, the more kind of interesting part is how to draw a rope that seems to kind of sag between two adjacent points, right? So in this example, we have a third point that we do not show to the user. Let's call it a virtual point, or on the scheme, it's like a red point, right? So this virtual point, which is red on the scheme, connects two adjacent dots or points, and they are form triangle. So two adjacent points and this red dot forming a triangle. And in order to draw this sagging line, you will need to use a Bezier curve. I mean, not need to, but you can use Bezier curve. And so we draw a Bezier curve from point 1 to point 2 through our virtual point 3. And that's how we get this sagging of the rope. And now let's take a look at how it's implemented in code. So first thing we need is some kind of path to draw a line. we wrap our path in remember, so the path instance is not recreated with each recomposition. And next, we declare canvas, which is also a composable function. And then we reset current path, move to point A. Next, draw path to point B through midpoint, our virtual point, like red dot, using the quadratic Bezier 2 function. Once path is ready, we can draw it on canvas. As we have already said, canvas is just a composable function, and so-called draw scope is available inside it. This means that you can draw like different objects and call various functions related to drawing. You can draw the same primitives as in Android views, like circles, rectangles, paths, colors, and so on. So at this stage, we have almost everything ready. All that remains is to add the animation, right? So we can kind of drag our points. We can see that our rope is sagging, but now let's add the animation. So a key here, or like a secret here, that we will animate just our virtual point, right? So the logic is that when we move one of the real points, the coordinate of the virtual is also changes. And we can actually change its coordinates with animation. And to do that, we can use the animate offset as state function. So every time the offset of a virtual point changes, instead of kind of strictly redrawing it, we animate this change, right? And the bounciness of this rope is achieved by using a special animation spec. The key here is that we are using a spring animation spec, so animation that kind of imitates the real physics behavior, and due to it, kind of this bounciness is achieved, right? And to be honest, I think writing similar animation on Views framework would be much more difficult, if not impossible, because Spring support is quite limited in Compose. So, what to remember when animating a canvas? So, canvas is just like a you should treat a canvas as just as a composable function, but we just have like a draw scope in it, and that's why we can draw some like I don't know, shapes and colors inside it, right? But other than that, it's just like a regular composable functions. And therefore, we can use all the animation primitives such as transitions, animate state functions, animatable, and so on and so forth with canvas, right? And we can animate various paths, circles, colors, and all of the canvas primitives. The main thing to keep an eye on is number of recompositions, whether we are doing too many of them and how optimally our code works. And I recommend also watching a video from Google with typical mistakes when working with Jetpack Compose, and a video about drawing in Compose. And yeah, there's links in the presentation, so you can click on them, and the presentation I will either send or it will probably be attached in somewhere in the event, so you will find it pretty easily. So all links in the presentation are clickable. So another question that is pretty interesting is performance, and here I tried to kind of compare the performance of the same animation, one which was written in Vue, and the other one is written in Compose. And I compared this only in release build type and with Minify enabled true setting. And this is like pure canvas based animations, and canvas was chosen because we have the kind of the greatest control over what's happening in canvas. And if we use some like high level animations, we don't know how they are implemented, and so the performance comparison will not be so fair. So that's why I decided to use a canvas. So I compared that on 3 phones, on three different devices. As I said, again, I compared that in release build type with Minify enabled setting true. And if you can see the profiler, like profiler graph, you can see like for views based graph is like slightly different than compose based graph, right? And we can see that in compose we have a green part of the graph just a bit wider than on the views based, right? And the green part is actually responsible for calculating animators and layouting. and which means that basically Compose, for some reason, takes a bit more time to calculate new animation value and layout items. You can actually check it yourself, and yeah, feel free to do that. But in reality, it's not noticeable. I tried on the different devices, on a very weak device, on a very strong device. All animations are working smoothly, and kind of you cannot distinguish between them, which is good news for Compose. But still, you can you need to keep in mind that in Compose it might be not as performant as in Views. And we can also use like GFix Info to check how much junky frames we have. Sorry. So in views-based animation, we have 0 junky frames out of 5,000 frames, and in compose-based, we have 1 frame, which is nothing, right? So, which means that everything is good. And now let's briefly discuss tests and testing of the animations. And we only have like 10 slides left, so we're pretty close to the end. So in order to for the necessary classes to be available, we need to connect or attach or add 2 dependencies, after which a special compose test rule will be available. So in the compose test rule, we have access to the main clock field, with which we are able to set required time of the animation. So if the animation takes, for example, 2000 milliseconds, we can literally kind of see frame by frame how it happens by setting this time. And it's also worth noting that all tests written using this compose test rule are UI tests, right? And you can test animations using screenshot tests. And for example, we can use like a shot library, right? So it's like a library written for a screenshot tests. So the logic is like this, right? So we take a screenshot, we compare this screenshot with a certain like a baseline screenshot. We increase time, we take screenshot again, compare it with a baseline screenshot again, and so on and so forth. And the test might look like this. So it must extend screenshot test class because some comparison methods will become available. And we will have a compose test rule declared inside the test and the test function itself. I'm sorry. And inside compose test rule, the set content function is available, in which we can actually call composable functions. There we can also turn off automatic clock ticking with line main clock auto advance of, equal false. So we turned off automatic clock, and we will kind of control clock manually. And then everything is pretty simple. We simply rewind the time and compare the current screenshot with the kind of reference or the baseline one. In this case, we rewind the time 2 times at 200 and 1400 milliseconds, but you can rewind it as much as you like, depending on your animation. I'm sorry about that. So after we develop the test, we need to prepare the standard screenshots that we will use for comparison. And if you need to execute, and to do that, you actually need to execute this Gradle task with this option prerecord. And after task is finished, standard or like a baseline screenshots will be available in some directory. And if we want to launch the tests, we also need to execute this command, but without prerecord parameter. And after that, a report will be generated where we can see what tests failed and why, and what's the different, like a diff between baseline and current value. Sorry about that. So yeah, I would like to say a few more words about the animation tooling. and I believe that any available tooling is better than nothing. So we actually have a pretty way to enable this tooling window that we can use for debugging our animations. And to do that, we need like a preview function. And if Android Studio recognizes some animations, this icon of like 3 circles will appear. And after clicking on it, the toolbox window will open, and all of the animations that Android Studio has recognized are available there. And you can play with them, like select, enter, exit, and basically play frame by frame. And in a specific animation, you can play it frame by frame, as I said. And to practice what we've just learned, I would highly recommend to visit the Google Animations Code Lab and pass it. It's like a very good set of lessons that you can pass one by one. And I'm pretty sure that it will be very useful if you want to learn the animations. And that was it from me. So you can ask questions now if you have any, and you can also find me in any like social network and like ask questions directly from me. I am very grateful that you come here. Thank you all for coming. I hope this talk would like was useful to you, and you will take some like useful knowledge from it today. And yeah, this is it. I am ready to answer any questions if you have any. I will stop presenting now. So yeah, you're welcome. You're welcome, guys. Yeah, maybe like no questions. You don't have a lot of questions now, but if you do, please kind of feel free to post them, probably in the event page, or like you have my like contacts in the presentation. You can like add me on LinkedIn or whatever, or in Telegram, and ask questions from me directly. And yeah, we will wait for a couple more minutes to if maybe someone will ask a question. If not, we will probably call it a day. Yeah, let me just type it here. So my Telegram is. There will be no questions for now. Again, thank you. Like huge thanks for everyone who participated today. I wish you all the best in learning Android. And again, if you want to reach out to me, feel free to do that. So thank you for coming. I wish you all like all the best and the kind of the best end of this Sunday and the productive work. So there's one question: when should we expect the next event? So I think it's like, so the events are in general hosted by this Codementor platform, and so I think they will kind of notify you in some way. So yeah, I'm not sure when the next event would be, but I think you will have to wait some notification from the Codementor platform itself. Yeah, thank you, Nazar. All the best to you as well. All right, let's call it a day. Again, all the best. See you guys. Cheers.